Now let's talk about logarithmic functions and logarithmic differentiations. This is going to be continued from inverse functions. That's where everything begins. First, let's begin with differentiation formula for inverse function. And here's a general formula. The derivative of an inverse function is 1 over the derivative of the original function. But then again, we may need some algebraic manipulations because of the inside part. This one looks very simple, but then again, some manipulation is necessary most of the time. A prime example is logarithmic function, and here's a formula. Derivative of natural logarithmic function is 1 over x, and then combine that with a chain rule, and the derivative of log of ux is u prime over u. It's going to be 1 over u of x, but you have to multiply u prime of x. So after simplification, you end up with u prime over u. How do we deduce that? Well, we begin with implicit y of log of x, and equivalently speaking, it can be written as e to the y power is equal to x. That's coming from the inverse function, of course. And then apply implicit differentiation. Basically, taking the exponential implicit differentiation, exponential stays the same, and then y prime pops out, and then taking the derivative of x by x, that's just 1. Consequently, y prime is equal to 1 over e to the y power. And what is e to the y power? It is just x. And that's how we can deduce the derivative formula for natural logarithmic function. Here I use German notation, Leibniz notation, which is preferred by our textbook author, but in my experience a lot of students prefer this prime notation better, so I use both. Okay, now that we talked about logarithmic functions and its derivative formulae, let's open it back up. Let's do some examples. The first example is just too simple. Let's do that very quickly. Let's simplify those logarithmic functions with log rules. 2 comes out, 3 comes out, and we have just 6 log of I. So derivative is 6 times 1 over y. It's too simple. The next one is a little bit more challenging, but still very standard, because if you use just log rule, then you can make this inside very simple. First, the simplification. Log function changes multiplication to addition and division to subtraction. So all those factors in numerator has positive log, and all those factors in denominator has negative log. Of course, the next step is to bring all those powers down. 1/2 comes down, and then 2 comes down, and then now we are ready to apply the derivative formulae. Let's go. The derivative is 2 times 1 over x, so that's settled. And the next, derivative of the second, this is u prime over u forms, so inside goes to denominator. By chain rule, you have to multiply the derivative of the inside, which is 2. Right over there, that formula. How about this one? X squared plus 1 is u inside, so that goes to denominator, and you have to multiply the derivative of the inside, that's 2x this time. There was 2 before because of this 1/2, so after cancellation we get something like that. Of course, if you do not cancel, if you stop here, as far as I'm concerned, I'm going to give you full credit, because that's nothing more than a little bit of algebra. If you're dealing with computer grading system, that's going to be a little bit annoying, so please be careful about those kind of things, and please be prepared to simplify whenever necessary. Okay, let's go over to logarithmic differentiation. And logarithmic differentiation is basically differentiation technique where you have to use the derivative formulae for logarithmic functions in the intermediate step. And let me copy that formula over here so that we are going to be used, so that we can consult a little bit more easily. And then let's move on. There are 2 types. One is very complicated multiplication and division type. 2 is kind of power and exponential, where both the base and exponent of functions. The first case, how to calculate the derivative of something like this. If you use quotient rule, then it's gonna be really annoying because this is too complicated. One way to handle that is to use generalized product rule, which personally I prefer. So how do you handle that? Change this quotient into product form by keeping all those numerators the same, and denominator, now look at these. We have negative powers and then we've flipped up everything. So we have product only, so let's use the generalized product rule. The derivative of the first function times the rest, the derivative of the second function times the rest, the derivative of the third function times the rest, and then the derivative of the fourth function times the rest. And of course, I don't really care anything about simplifications, so if you stop here, you're gonna get full credit. And personally, I prefer this answer. However, the reality is, many of you may have to take state exam, and the state exam is multiple choice, and then you have choices A, B, C, and D, and none of them looks anywhere like the form you just did. Then you're going to be in trouble. So I don't think it is very educational to limit the student's method, but when you're dealing with multiple choice, you can't help it. So I'm going to compromise my teaching philosophy and talk about this logarithmic differentiation. So coming back again, just for my courses, you don't really have to use both of those methods, but for state exams, you'll have to study this. Okay, how does it go? Start from taking a logarithm. So if you take the log of this complicated bunch, then you can use log rule to simplify like this. New factors in numerators are added, factors in denominators are subtracted. That's because of the log rule. And the next, power comes out, power comes out, power comes out, power comes out as coefficient. Actually, this one, log and exponential canceled, as a matter of fact. So we are ready. Everything is all simple. And then let's take the derivative using this one, u prime over u rule. So the derivative of log of y will be y prime over y. And the derivative of x is 1. Derivative of this one, 3 is coefficient, and 1 over x plus 2. That's it. Derivative of the inside is just 1. How about this one? Derivative of x squared plus 1 goes down, and derivative of the inside is actually 2x. But then again, 4 was there before. So after simplifying, you're going to get 8x. How about this one? 4 was there before, and then multiply by the derivative of the inside. That's how you get 12 there. But don't stop here, because this is a derivative of log of y, not the derivative of this, y prime. And y prime is this numerator, so all you have to do is flip this y to the other side. So y prime is y times something you just calculated. But wait a minute, what is y? That's original problem. So rewriting that original problem, we have that complicated bunch times the computation you did. This completes the logarithmic differentiation process. By the way, if you see a multiple choice problem, you'll be able to eliminate out of 4, maybe 5 choices, maybe 2 or 3 of them, simply by looking at this part. This times something, and that part should be exactly the same as before. That's the structure of logarithmic differentiation. I'll leave the second problem to you, and of course, a Weber sign Homer problem has more. I'll just show you the first step. If you take the logarithm, if you take the log, oh come on, if you take the log, then we have log of that big square root. So square root is 1/2 power. So 1/2 comes out and we have something like that. And then if you simplify the same fashion, numerator, numerator, denominator, denominator, numerators added, denominator subtracted. Well, please remember 1/2 applies to all these because 1/2 was here before, which originally came from that square root actually. I'll leave the detail to students. Let's move on to the other type of logarithmic differentiation, and those are these types. Let's move this here for convenience. Okay, x to the log of x power. This log of x is just coincidence. I could have given you x to the x power, x to the cosine of x power, tangent of x to the sine of x power. It may not have anything directly to do with log, but still log rule applies. There are two ways to handle this problem. One is logarithmic differentiation, and the other is change of base formula. And let's move on to logarithmic differentiation first. Standard technique is to take the log first. So here we go. Taking the log of that, log of y is log of x to the log of x power. And then log rule applies. Power comes out. So log of x comes out, and then log of x, so log of x squared. Now let's take the derivative. Left hand side is implicit differentiation. 1 of y times y prime. So as usual, you have y prime over y. Right hand side, using the chain rule, 2 comes out, log of x stays. First power, so I don't have to write it. By chain rule, I have to multiply 1 over x. After simplification, we get that. And then flipping this y to the other side. So y times that computation will be my answer. And please remember what the y was. Y was the original problem. So copying that, we're going to get an answer. X log of x power times computation I did. And then a little bit of further simplification because this is negative first power. But the final simplification is not really necessary. That's a log rule computation. The second method is to use the change of base formula. And it's based upon the change of base formula, this. A to the b power is the same as exponential of b power times log of a. And then of course, if a and b are both functions, then exponential is exponential, and we're going to have function only up there. So prepare to use product rule or something like that. So here we go. I can change x to the log of x power as e to the log of x and log of x. We have two logs, but log of x was there before. And the second is coming from this log of a. So after simplification, I give e to the log of x squared. Maybe I'd better expand the font. Okay, that's better. And then let's go ahead and take the derivative using the chain rule. Y prime is, well, okay. So log function, exponential function, excuse me, stay the same. And all I have to do is take the derivative of the inside. And that is log of x squared function. So 2 log of x. And then multiply the derivative of the inside, 1 over x. And as a matter of fact, all the simplification here is not necessary here. Just exponential, and then this computation is enough. So this change of basis formula yields actually a simpler solution. Personally, I like this one better. As far as my personal preference is concerned, maybe you can say that I do not like logarithmic differentiation at all, because in first type of problems, I generally prefer generalized product rule. And for second type, I prefer the change of base formula. But then again, logarithmic differentiation is often necessary because of those multiple choice exams mandated by Texas or all kind of state exams, GRE sometimes. So can't be helped. Please study both.